they could not be here, but since I was the one that was here, I have been chosen to give the presentation. LADEE is a moon mission and was just recently launched. And it's actually the objective of the mission is to measure the lunar dust, to characterize the lunar atmosphere, and it's actually about a 100-day mission with contributions from both Ames Research Center from NASA, Ames, and NASA Goddard Space Flight Center. And it has 3 major instruments and 1 major technology payload, which is the laser communications, the first launch on a Minotaur 5 launch vehicle from Wallace. So, one of the things, why are we doing this mission? Why is it important for us to do this mission? Well, one of the things we wanted to do is understand more about the Earth's atmosphere. But to understand more about the Earth's atmosphere, we also need to understand more about the atmosphere of many of the other planets. And it turns out that most planets, such as the Moon, or it's not a planet, or Mercury, Venus, and most other planets, they have this kind of exosphere type of environment, of atmosphere. You know, very rare, not much gases around. So essentially, these exospheres are largely still remaining a mystery. You know, their density varies month to month, appears to increase and decrease, as you can see, for example, for sodium. And also for the case of the Moon, you have hydrogen that probably is bouncing off from water molecules that are changing. And are other species variable or not? What happens? And how does that compare to the Earth's atmosphere? So if we can understand more what's happening in the Moon's atmosphere, then we can also understand what's happening to us. We also can understand the type of exospheres that you would have in asteroids. We're talking about sending humans to asteroids. So we need to understand how that exospheres of the asteroids change, what's in there, what are the compounds, what exists on those exospheres. So this becomes extremely important from a scientific point of view in study. And the closest body that has this kind of exosphere is the Moon. And again, it still remains a mystery, even though we have been to the Moon in the 70s, we still do not know exactly how this exosphere behaves. So the goal of the mission then is to determine the global density, the composition, the time variability of the fragile lunar atmosphere, the exosphere, you know, before it's perturbed by further human activity. We want to determine the size, the charge, the spatial distribution of the electrostatically transported dust grains. In addition to the science, which is going to help us understand our atmosphere and also understand the atmospheres of such places as Mercury or asteroids. So in addition to the science, we're also going to do test laser communications, because laser communications is going to become extremely important for future human exploration because of the high data rate that laser communications can bring to the Earth. And also, in this case here, we also wanted to demonstrate a low-cost lunar mission with a reusable bus and made of modular sections. So there were several aspects of these missions that are important to us as we move into more space exploration. So the key principle then is, is to follow a low-cost approach, minimize complexity, of course, accept some risk of minimal hardware, and try to execute the mission as a cost cap. All right, the key instruments up on the top left is the neutral mass spectrometer with the acronym NMS. It's an in situ measurement of the exospheric species. It's done by NASA Goddard. So a very important instrument as a mass spectrometer, similar to other spectrometers that we have flown on Mars missions like the SAM, which is a major spectrometer on the Curiosity rover. To my right here, you have ultraviolet visible spectrometer, where you can measure wavelengths from 0.2 to point 8, and it's done by NASA Ames to actually look at the spectrum of the wavelengths coming out from the atmosphere. On the left is an experiment to actually measure the lunar dust, so we can understand better what happens to the lunar dust, because one of the things we understand is that the lunar dust is highly charged, it's electrostatically charged, and that kind of dust seems to get into all kinds of equipment. So if we're going to return to the moon, we need to understand the impact this dust does in actually in the wear and tear of mechanical equipment. So understanding better what it does will be very important for if we go ahead and do future moon exploration. And to the right, we have the lunar laser communication demonstrator. It's a technology demonstration. The first laser demonstration done by NASA, which has a capability of about 50 to 600 megabits per second from the lunar surface. And that's done by Lincoln Laboratories, and the lunar dust is done by the Lunar Science Laboratory at the University of Colorado. So I'm going to talk a little bit more about the laser comb. I chose the laser comb as one of the easier one to talk about, since the science you can find in many of the press kits and many of the other areas, and also an area that I'm a little more familiar with, easier to explain for me. So basically what we have is a laser terminal on the spacecraft. That laser terminal is going to try to talk to a terminal on the ground that's going to exist at white sand. The red beam coming up is what we call the laser beacon, to tell the spacecraft, here's where I am on the ground, you need to point to this particular location. Then the spacecraft starts transmitting to the ground. So the top piece on the top is the beacon, and the other 4 elements at the bottom are the actual receivers. So what we have then is the uplink, which is a very powerful 10-watt laser, 4 10-watt lasers, going into a 10 centimeters telescope on the spacecraft. And the rate of transmission from that uplink is somewhere between 10 to 20 megabits per second. So that's the uplink. The downlink, where you're going to bring your science information and so on, is done again at the 1.55 wavelength, with about a half watt, a 10 centimeters laser on a telescope on the spacecraft, and it has the capability of transmitting between 40 to 620 megabits per second to the ground. In addition to this main station at White Sands, we also have 2 additional stations that could be potential. One at JPL called the Table Mountain in California, and then another one from ISA, the Tenerife, Spain. So both stations will also have the capability to receive the signal from the optical communication system in case there are problems with the White Sands station. And the importance of this element, or this demonstration, is also the fact that this lunar laser communication system will serve as a pathfinder for a much more ambitious, larger system that NASA is planning to fly in 2017, called the NASA Laser Communication Relay Demonstration, LCRD. Okay, so here's an overall picture of the spacecraft with, on the top, the 4 major instruments: the LDX for the dust, the UVS for the ultraviolet and visible measurements. On the side of the mass spectrometer, on the my right side here, the laser communications, and the thrusters at the bottom. So this gives you an overview of the spacecraft. Well, here is the spacecraft progressing into encapsulation and then getting ready on top of the rocket. Okay, and here is almost getting ready for launch from the Wallops facility in Virginia. This is, as I mentioned earlier at the very beginning, the first ever flight on a Minotaur 5. It's a 5-stage solid rocket motor derived from a converted Peacekeeper intercontinental ballistic missile. So the very first flight, and was very successful. You'll see a couple of pictures in a minute. So just talking about the mission a little bit. The mission has a series of phases with, of course, different orbits. In particular, we have the launch and ascent, which took place in the past week or two. Then you start doing the phasing orbit. We're going to try to do 3 orbits around the Earth before actually getting injected into the lunar orbit. Then you have the commissioning phase that will last about 60 days. And then after the commissioning phase, you have the science phase that's about 100 days. And then the decommissioning, which will be approximately 1 day or so, or less than a day, where the spacecraft again will crash into the surface of the moon. So, again, we are now going around the Earth and start getting into the lunar insertion orbit to go towards the moon. And the science operations, essentially each orbit is about 114, 116 minutes per orbit. So essentially in our 24 hours, you have about 13 orbits. So essentially then doing those 13 orbits, you have different instruments doing investigation. So, and then with periods for communications and some periods for orbit. But that's basically the science operations will be 100 days with about 13 orbits during our own 24 hours, with each orbit lasting about 114 to 116 minutes or so, in different instruments, then again, doing different orbits. Okay, here a very successful launch on September 6th at 11:27 p.m. out of Wallops. And then a very nice picture taken out of the Rockefeller Center in New York. As you could see, the rocket going over the skylines of New York City. And a spectacular launch, very successful, and a very beautiful picture. So where are we on the mission so far? We're just in the beginning. We had some minor safe modes. So essentially, there was a successful recovery of the first safe mode immediately after launch because of the reaction wheels current increase. They were powered down by the spacecraft, initiated again with no problems. So the spacecraft is doing well with the reaction wheels. Then we had another second entry safe mode due to an alignment error between the Star Tracker cameras. That was resolved. We found the error and recovered from safe mode with no problems. The cameras are working well. The reaction wheels are working extremely well. We also have done a successful execution of the first apogee maneuver 1 and the perigee maneuver 1 also. We have checked out the key instruments, the mass spectrometer, the dust experiment, the UV spectrometer, and they're all performing as expected. We also have done the very first electronic check of the laser communications. We operated for about 28 minutes. It's alive. It seems to be okay. There was no transmission of the laser phone, but just checking of the system, it seems to be performing quite well. So the Minotaur 5 and the LADEE spacecraft performance to date are excellent, and we are really looking forward to a successful science space mission. So there is a great science, very important science from the aspect of understanding this exosphere type of atmosphere, to understand a little bit of what happens to the water, because it looks like there is migration of the water from the equator to the poles, and sometimes of this water, the molecules get separated, and that's where you have the hydrogen. So if we can measure some of the hydrogen, that's important to understand what's happening to the water. It's important to understand what are the molecules, what are the gases that are actually existing in the surface of the moon, so we can translate that information to understand more about our atmosphere, understand the atmosphere of most of the other planets, such as Mercury, Venus, and also the asteroids. And then also trying to understand about the dust, the impact of the dust. Why is the dust so sticky? And why is so fine? And what impact does this dust have on the electronic equipment or mechanical equipment? And in particular, if we want to put a lunar base or send future missions to the moon. So very important in understanding the dust. So this mission within 100 days will try to answer some of those key questions for us. So on our way to the moon, LADEE seems to be going quite successful. Stay tuned. There are many websites from NASA Ames Research Center that will be providing you updated information, sometimes on a daily basis, of what's coming out from the mission. Thank you.